Bill Bryson, A Short History of Nearly Everything. Prepare to embark on a journey through time, space, and the mysteries of our universe, guided by the captivating narrative of Bill Bryson's A Short History of Nearly Everything. This engaging book summary will take you deep into the scientific knowledge, remarkable discoveries, and untold stories of Earth, its inhabitants, and the cosmos. You'll explore fascinating themes such as the Big Bang, the vastness of the universe, the elusive search for extraterrestrial life, and the groundbreaking contributions by Isaac Newton, Albert Einstein, and Werner Heisenberg. In addition, you'll get a glimpse into the interconnected realms of geology, oceanography, photosynthesis, genetics, and potential threats to Earth's existence.
Chance discovery of cosmic hiss. In 1965, radio astronomers Arno Penzias and Robert Wilson stumbled upon a persistent hiss while trying to find radio silence for their experiments. It turned out to be cosmic background radiation, evidence of the Big Bang, the moment the universe was born. Inside an incredibly dense point, all the building blocks of the universe were suddenly flung, expanding faster than the speed of light. In just 3 minutes, the universe became billions of light-years in diameter, and 98% of all matter was created. This cosmic hiss is even detectable via a detuned television set, a remnant from the earliest moments of the universe. In 1965, Arno Penzias and Robert Wilson, two radio astronomers, were searching for radio silence in New Jersey to conduct experiments. However, they continuously encountered an indistinct hiss, difficult to eliminate by any means. After exhausting all options, the pair reached out to astrophysicist Robert Dicke at Princeton. Upon hearing their story, Dicke instantly recognized the significance of the mysterious sound. It was cosmic background radiation from the universe's birth. Unintentionally, Penzias and Wilson unearthed the first concrete evidence of the Big Bang. According to the Big Bang theory, the universe sprouted from an unimaginably dense point, expanding at an astonishing pace. This single point, known as a singularity, contained all the building blocks of the universe. Then, suddenly, the singularity burst open, flinging everything across the vast expanse of space. The scale and speed of the explosion are mind-boggling. Just after the Big Bang, the universe doubled in size every 10⁻34 seconds. To help visualize this rapid expansion, consider that within 3 minutes, the universe grew from a minuscule speck to a size of over 100 billion light-years in diameter. In that brief time, it produced 98% of all matter and the fundamental forces governing the universe. Returning to Penzias and Wilson's discovery, we may ask what exactly caused the persistent hiss they found. The intense energy from the Big Bang eventually cooled and transformed into microwaves, which manifested as the hiss they detected. Strikingly, anyone can perceive this evidence with a simple television. Tune your TV between stations, and listen to the strange static noise. 1% of that is a remnant of the Big Bang, a relic of our universe's genesis. Quest to find cosmic neighbors. In the unfathomable expanse of the universe, teeming with billions of galaxies and stars, the likelihood of extraterrestrial civilizations seems increasingly plausible. The Drake equation, developed in 1961, supports this possibility by calculating the number of advanced civilizations that could exist in our galaxy. However, distances measured in light-years make potential encounters a distant dream. The sheer scale of the universe, birthed from the inconceivably minute singularity into a Goliath spanning 1 million miles, is astounding. To comprehend this vastness, imagine 140 billion frozen peas, the same number as known galaxies, filling an enormous auditorium. In our own galaxy, the Milky Way, estimate places the number of stars between 100 and 400 billion. Faced with this staggering celestial expanse, the notion that we are alone in the universe seems far-fetched. To determine the potential existence of alien civilizations, Frank Drake, a professor, developed the Drake equation in 1961 by dividing key variables, stars supporting planetary systems, systems nurturing life, and planets where intelligent life could evolve. Surprisingly, his estimation revealed a multitude of advanced civilizations in our own galaxy, possibly in the millions. However, excitement about possible encounters with extraterrestrial neighbors should be tempered by the enormity of space. Light-years separate potential civilizations, with an average distance of 200 light-years between hypothetical neighbors. Considering that 1 light-year equates to 5.8 trillion miles, these alien worlds are likely too distant for the human race to witness any time soon. Nevertheless, the cosmic vastness challenges us to question our own existence and imagine a universe teeming with diverse life. Unraveling Newton's scientific genius. Isaac Newton, an eccentric yet brilliant individual, dedicated his life to advancing science. His most vital work, Philosophiae Naturalis Principia Mathematica, or Principia, delved into the mysteries of the universe and Earth's movements. Thanks to Newton's groundbreaking ideas, such as the universal law of gravitation, scientists gained significant understanding of the cosmos and our planet's composition. Newton revealed Earth's true shape as an oblate spheroid and enhanced our knowledge about its motion. However, the enigmatic scientist never divulged any information regarding Earth's age. Isaac Newton's unwavering commitment to scientific advancement set him apart from others in his field, even if it meant risking his own well-being. Undertaking daring experiments, such as probing the mechanics of vision by inserting a needle into his eye or gazing at the sun to test ocular limits, he established himself as a peculiar yet exceptional thinker. Newton's main focus centered around making sense of the universe's and Earth's motion. His magnum opus, Principia, remains widely regarded as one of the most profound scientific works in history. Although deliberately challenging to interpret for lay people, those with the intellectual capacity to decipher it obtain access to Newton's revolutionary concepts. In Principia, Newton introduced the universal law of gravitation, which denotes that all bodies, regardless of size, attract every other body in proportion to their mass. This law explains why massive stars generate a strong enough gravitational pull to bring planets into orbit, while smaller objects like desk lamps exert a much weaker force, preventing items like pencils from orbiting around them. Newton's insights within Principia allowed scientists to decipher Earth's weight, approximately 5.9725 billion trillion metric tons, and determine its true shape, an oblate spheroid with slight flattening at the poles and a bulge at the equator. Despite revealing crucial information about Earth's motion and form, Newton left the riddle of the planet's age untouched for future exploration. Unraveling Earth's true age. Long before a definitive answer was established, scientists sought to determine the Earth's age. While Irish Archbishop James Ussher estimated its creation in 4004 BCE using the Old Testament, 19th-century geologists relied on rocks and fossils, deducing Earth's age to be millions of years. The key to unlocking Earth's precise age came from radioactivity, discovered by Marie and Pierre Curie in 1896. Physicist Ernest Rutherford expanded on this discovery, finding that unstable elements decay into other elements over a consistent span of time, known as half-life. Ultimately, in 1956, Claire Cameron Patterson used a dating method based on ancient meteorites to reveal that the Earth is approximately 4.55 billion years old. In 1650, Irish Archbishop James Ussher attempted to answer a burning question: how old was the Earth? Using the Old Testament and historical documents, he claimed it was created on October 23, 4004 BCE. Most scientists disagreed, believing Earth to be far older but lacking the means to determine its exact age. Geologists from the 19th century examined Earth's rocks and deduced from the layers that there were numerous geological periods spanning millions of years. However, the precise age of the Earth still eluded them. That is until radioactivity entered the scene in the 20th century, which ultimately revealed Earth's true age. In 1896, Marie and Pierre Curie discovered that certain rocks radiated energy without altering their size or shape, a phenomenon they named radioactivity. Physicist Ernest Rutherford was intrigued by this groundbreaking discovery, and through further research, he found that radioactive elements eventually decayed into other elements at a constant rate. For example, uranium-235 consistently decays into lead-207, a transformation termed half-life, which proved valuable for estimating the age of substances. Knowing the half-life of uranium-235 and understanding that it decays into lead-207 allows for accurately calculating a rock's age based on the current amount of these elements present. Claire Cameron Patterson, a talented scientist, unified these discoveries in 1956, developing a precise dating method using ancient meteorites. He concluded that Earth was approximately 4.55 billion years old, with a variable of 70 million years. This age deviated significantly from Usher's estimation and provided a definitive answer to an age-old question. Through groundbreaking scientific discoveries and innovative research, humanity has managed to unravel the mystery behind Earth's age. From the initial estimates based on religious texts to complex dating methods rooted in radioactivity, the knowledge of Earth's age has solidified over time. Today, we recognize our planet's age as approximately 4.55 billion years, a testament to the evolving nature of scientific understanding. Time's relativity unveiled. Albert Einstein, despite a less-than-stellar academic beginning, revolutionized science with his special theory of relativity. This groundbreaking concept challenges the notion that time progresses at a constant speed, asserting that it is instead dependent on one's relative position and velocity. Albert Einstein, one of the most iconic scientists in history, initially faced challenges in his academic journey. Surprisingly, he failed his first college entrance exam, and after studying to become a high school science teacher, struggled to secure a job in his chosen field. Eventually, he took on a position at the Swiss Patent Office. It was here, in 1905, that Einstein made an indelible mark on the world by publishing papers that would fundamentally alter the scientific landscape. Of particular note, he introduced his groundbreaking special theory of relativity, which states that the passage of time is relative, rather than constant. This idea defies our everyday experience, as time seemingly progresses at a consistent pace without deviation. But the truth is, time can and does pass at varying speeds based on unique circumstances, specifically our positional and velocity relative to another person or object. To better grasp this mind-bending concept, consider a thought experiment devised by British philosopher Bertrand Russell. Imagine you're at a train station, observing a train approaching at nearly the speed of light. To you, the train would appear distorted, with voices inside sounding muffled and slow, akin to a sluggish vinyl record. If you were to see any clocks within the train, they would appear to tick slower than the one on the platform. The strange aspect of this phenomenon is that travelers inside the train would experience everything as usual, with no noticeable distortions or changes in the passage of time. However, if they looked at you on the platform, they would perceive you as the one experiencing time's distortion. Hence, the speed and our relative position to a moving object dictate how we perceive the passage of time. This astounding revelation is just the beginning of Einstein's contributions to science, with further discussion to delve into his next revolutionary discovery. Unraveling gravity's mysteries. We possess an incredible amount of energy within ourselves, with potential energy existing in every atom and molecule of our bodies. This energy, linking mass and energy, is explained by Albert Einstein's famous formula, E=mc². However, Einstein's work went beyond this discovery, as he also introduced the groundbreaking concept of spacetime, completely altering our understanding of gravity. By considering space and time as part of the same entity, he unveiled a new way of understanding how massive objects create gravity by bending spacetime. Our bodies are made up of atoms and molecules containing massive amounts of potential energy. In fact, releasing all the energy within you would cause an explosion equivalent to 30 hydrogen bombs. The incredible connection between mass and energy is depicted in Einstein's well-known equation, E=mc², which states that energy equals mass times the speed of light squared. Essentially, this concept reveals that mass and energy are intertwined, with mass representing potential energy ready for release. Einstein's noteworthy endeavors didn't stop there. His general theory of relativity, published in 1917, presented the groundbreaking idea of spacetime. Spacetime merges the three dimensions of space with a fourth dimension, time, resulting in a single entity that intertwines both elements. While it's challenging to picture spacetime, envision it as a malleable sheet of rubber that bends and warps. This innovative idea of spacetime forever changed our perception of gravity. Gravity is, in fact, the curving of spacetime itself. Here's how this fascinating process unfolds. Objects with mass bend spacetime, with more massive objects creating more significant curvature. Smaller objects passing through spacetime are influenced by these curves, and, in simple terms, this is what we know as gravity. To further illustrate this concept, imagine placing a bowling ball in the middle of a sheet of rubber. The sheet will stretch and sag under the weight, similar to how large objects like the sun distort spacetime. Now, picture rolling a marble across the sheet. Although the marble's trajectory initially appears straight, it veers off course when approaching the bowling ball, following the slope created by the heavier object. This motion resembles planets orbiting the sun, as the marble circles the curve in the rubber sheet. Through his general theory of relativity, Albert Einstein elegantly unveiled the true workings of gravity, transforming our understanding of the cosmos and the forces that shape it. Heisenberg's uncertainty principle. When delving into the world of atoms, molecules, and particles, Einstein's theories don't quite encompass their behavior. Werner Heisenberg's uncertainty principle contributes to our understanding of how particles move, particularly within atoms. Created as a part of quantum theory in 1926, Heisenberg's principle posits that electrons can be both particles and waves. This principle also explains that we can know an electron's position or its path but cannot know both simultaneously. Consequently, quantum physics and the theory of relativity coexist to explain the universe. However, no single theory manages to encapsulate everything yet. Albert Einstein's groundbreaking theories immensely improved our comprehension of large-scale phenomena like time and gravity. But how well do these theories apply to the atomic and subatomic realms, such as atoms, molecules, and particles? As it turns out, Einstein's laws can't quite explain the curiosities found within these tiny systems. The mysterious motion of particles finds its explanation in Werner Heisenberg's uncertainty principle, a crucial component of quantum theory. Atoms consist of a nucleus, containing neutrons and protons, with electrons orbiting around them. The behavior of protons and electrons puzzled early scientists, as traditional physics couldn't account for the electrons continually orbiting without losing energy or the protons packed inside the nucleus without repelling each other. To tackle the complexities of the atomic world, a new branch of science emerged, quantum theory. A key contributor to this field was Werner Heisenberg, who formulated the concept of quantum mechanics in 1926. Central to his theory was the uncertainty principle. When physicists initially studied electrons' movement around the nucleus, they observed a peculiar phenomenon: electrons appeared to behave like both waves and particles. This baffled researchers, questioning how electrons could assume both forms simultaneously. Heisenberg's insight revealed that an electron is a particle that can be described similarly to a wave. Furthermore, the principle explains that we can either determine an electron's current position or its path and speed, but not both. Although quantum theory helps demystify subatomic processes, its applications are limited when examining expansive concepts like gravity and time. Conversely, the theory of relativity excels in explaining large-scale forces but falls short in addressing the subatomic domain. Consequently, science depends on two separate theories: quantum physics and the theory of relativity, each offering value in specific areas, but both unable to provide a comprehensive understanding of the universe. Earth's 4 life-sustaining criteria. As abundant as life seems on our planet, Earth is not as hospitable as it appears. In fact, humans can only inhabit a tiny fraction of the world's habitable space. Remarkably, specific criteria allow life to flourish on Earth. First, the planet must sit at an ideal distance from a star to maintain a conducive temperature for life. Secondly, Earth's molten core generates a protective atmosphere to shield life from cosmic radiation. Third, our appropriately sized moon stabilizes Earth's spin, ensuring a stable climate and weather. Lastly, the precise timing of events in Earth's history, such as the formation of the moon, played crucial roles in creating and sustaining life. Planet Earth, a beautiful mosaic teeming with life forms that coexist and rely on one another. Birds, insects, mammals, and humans all contribute to the rich tapestry of life. However, the real picture contradicts this seemingly idyllic outlook, and life on Earth required 4 unique criteria to emerge and thrive. Existing on Earth is a challenging task, with vast areas of our planet being inhospitable for human life. Deserts, oceans, and Antarctica account for the majority of the Earth, leaving us with a meager 0.5% of habitable space. It's a miracle to have even this fraction to call home. Overcoming this tremendous adversity, life springs forth thanks to 4 crucial elements. Firstly, the positioning of the Earth is perfectly balanced, nestling at the right distance from the Sun. If it were 5% closer or 15% farther away, life couldn't have developed, making our position the perfect Goldilocks zone. Secondly, Earth's atmosphere, an unsung hero, provides protection from lethal cosmic radiation. The molten core acts as the protagonist, generating a shield powerful enough to sustain life above the surface. Thirdly, Earth's celestial dance partner, the Moon, holds tremendous importance too. The Moon's ideal size and distance help slow Earth's rotation, preventing an unstable and chaotic climate. Without this cosmic companion, life as we know it would be utterly different. Lastly, timing is the essence of life on Earth. Life's genesis was only possible through an intricate sequence of events that played out over billions of years. Notably, our Moon was forged when a Mars-sized planet collided with Earth around 4.4 billion years ago. This cataclysmic event gifted us the perfect Moon, just in the nick of time. Had it occurred later, life on Earth could have been wiped out entirely. In conclusion, the vibrant existence of life on Earth can be attributed to these 4 fundamental criteria. Our place in the universe is indeed an extraordinary feat, worthy of reflection, gratitude, and a sense of responsibility. Earth's rare nature highlights the importance of preserving life and our environment for future generations. So, the next time you step outside, pause to appreciate the delicate balance that enables life to flourish on this pale blue dot. Unraveling Ocean's Mysteries. The Earth's oceans remain largely unexplored despite holding 97% of the planet's water. The first investigation of oceans dates back to 1872, resulting in the birth of oceanography. However, it took decades to garner more interest, as evidenced by Otis Barton and William Beebe in the 1930s, who broke diving records with their bathysphere. Although they lacked formal oceanography training and provided limited findings, their efforts highlight the importance of increased ocean exploration. The seemingly boundless oceans cover over 70% of our planet, a staggering 1.3 billion cubic kilometers of water. Despite this immense expanse, our understanding of life beneath the waves remains severely limited. Oceanography, the scientific study of Earth's oceans, was first established in 1872 when the British sent HMS Challenger around the world to survey the seas. Over a period of 3.5 years, the Challenger crew collected marine specimens, made measurements, and eventually compiled their findings into a 50-volume report. However, it would take several more decades for the next groundbreaking development in ocean exploration. In the 1930s, Otis Barton and William Beebe set out to investigate the depths of the ocean. With their homemade iron submarine, the bathysphere, they traveled far beyond our current diving capabilities. This simple, cable-suspended vessel held no propulsion or steering system, yet managed to carry the duo to a then-world record 183 meters deep in 1930, and over 900 meters by 1934. Despite these impressive achievements, Barton and Beebe were not trained oceanographers, meaning their observations weren't as impactful as they could have been. Furthermore, the scarce lighting in the bathysphere restricted visibility, rendering their findings insufficient for extensive scientific analysis. In the present day, while scientists have managed to reach the deepest ocean floors, substantial gaps in our understanding persist. In fact, we have more comprehensive maps of Mars than we do of our own seabeds. Estimates suggest that humans have investigated only a millionth, or possibly just a billionth, of the vast ocean depths. This underscores the importance of continued ocean exploration, as unlocking the secrets of the deep may hold invaluable insights into Earth's history and the potential for future discoveries. Bacteria, abundant and essential. From childhood, we are taught to wash our hands to eliminate bacteria and germs. However, bacteria are ubiquitous, and not all of them are harmful. In fact, bacteria play a crucial role in our survival by recycling waste, purifying water, and maintaining soil fertility. They also help in converting our food into essential nutrients and utilizing atmospheric nitrogen. Although a small fraction of bacteria can be pathogenic and cause deadly illnesses, most are neutral or beneficial to human health. We have been brought up to diligently wash our hands with soap and water to ward off disease-causing bacteria. While maintaining personal hygiene is indeed significant, it is impossible to completely escape bacteria since they are omnipresent. Bacteria are Earth's most prolific life forms, and our very existence depends on them. A healthy human skin alone hosts a staggering 1 trillion bacterial organisms. When compared to all living beings on this planet, the minuscule bacteria contribute to 80% of the collective mass. Now, you might wonder how bacteria manage to become so widespread. The secret lies in their exceptional reproductive efficiency. A new bacterial generation can be spawned in less than 10 minutes, making their exponential growth almost unimaginable in a matter of days. Moreover, they possess incredible resilience and adaptability, as demonstrated by their survival in extreme environments like nuclear reactor waste tanks. Even when faced with radiation, the DNA of certain bacteria can regenerate as if unharmed. The idea of coexistence with these microscopic organisms may initially seem unsettling. However, the reality is that bacteria have a predominantly beneficial impact on our lives. For instance, bacteria recycle waste, purify water, and promote soil fertility. They facilitate the breakdown of food, resulting in essential vitamins and sugars, and are crucial in the process of nitrogen fixation. While most bacteria pose no threat or even prove advantageous to humans, it is important to note that a tiny percentage, approximately 1 in 1,000, are pathogenic. They rank as the third deadliest killer of humans globally, causing severe illnesses like the bubonic plague and tuberculosis. This fact further underscores the significance of proper handwashing and hygiene practices. The Big Birth, life's origins. Imagine a kitchen where ingredients spontaneously mix, bake, and multiply, producing a growing number of cakes. This seemingly impossible scenario parallels the formation of proteins from amino acids, which are crucial building blocks of life. Spontaneous life began with a bundle of genetic material learning to duplicate itself, an event dubbed the Big Birth. This led to the creation of bacteria, which eventually harnessed water molecules, prompting the process of photosynthesis and an oxygen-rich environment for complex life forms. This marked the beginning of life's continuous evolution on Earth. In the peculiar world of automatic cake-making, ingredients surprisingly combine, bake, and multiply, spawning a constant supply of delicious treats. Although this impossible idea baffles our minds, it strikingly mirrors the amalgamation of amino acids into proteins, a vital process in building the foundation of life. Humans and life itself started from a spontaneous source, a genetic parcel that figured out self-replication, a single event referred to as the Big Birth. Such self-assembling processes are visible throughout nature, from symmetric snowflakes to Saturn's rings. When organic and inorganic ingredients, carbon, hydrogen, oxygen, and nitrogen, are so similar, why wouldn't spontaneous life evolve? However, this fascinating concept doesn't cover the specifics of how and why it all transpired here on Earth. Life traces back to a monumental breakthrough, the division of a small chemical bundle that subsequently passed on its genetic blueprint. Since that defining moment 4 billion years ago, life has persistently evolved. Bacteria were the first to emerge, reigning as Earth's sole inhabitants for 2 billion years. Eventually, these microscopic life forms unlocked the power of water molecules, giving birth to the process of photosynthesis and producing oxygen in Earth's atmosphere. Once oxygen levels paralleled contemporary rates, more complex life forms emerged, evolving into two primary categories: the oxygen-producing plants and the oxygen-consuming creatures like us. As we journey through time, the beautiful story of life's evolution unravels, stirring our curiosity about the next phase in this wondrous tale. United in Earth's diversity. Life on Earth started around 4 billion years ago when molecular bundles became capable of dividing and sharing their genetic code. Today, species on our planet are estimated to number anywhere from 3 million to 200 million, potentially leaving 97% of them undiscovered. All life forms, despite their massive variety, are interconnected, as proposed by Charles Darwin's On the Origin of Species, which discussed the concept of natural selection and evolution. Modern DNA research further emphasizes this interconnectedness by revealing genetic similarities among species, including a surprising percentage of shared DNA between humans and organisms like bananas, fruit flies, and mice. Moreover, certain DNA sequences can be interchanged between species, exemplifying the profound connections among Earth's living beings. This incredible diversity of life raises the question: could this miraculous phenomenon suddenly come to an end? Earth's unexpected perils. We often overlook the hazards that exist within our solar system and on our own planet, which could pose existential threats to humankind. The Earth is constantly at risk of colliding with the numerous asteroids that roam our solar system. These space rocks, millions of which are large enough to imperil civilizations, frequently come perilously close to Earth. However, potential dangers also lie much closer to home, such as earthquakes and volcanic eruptions that can have a devastating impact on cities and populations. Our planet's history is filled with instances of destruction, reminding us of the luck and fragility of our existence. The Earth's position in the solar system may convey a deceptive sense of security. In reality, our planetary home is subject to a multitude of risks. For example, asteroids are abundant throughout our celestial neighborhood, with over 1 billion in various orbits, many making regular close passes by Earth. Some of these asteroids are astonishingly large, with about 100 million of them exceeding 10 meters in width, while approximately 2,000 could potentially jeopardize human civilization. Surprisingly, near misses with these threatening objects may occur multiple times a week without our knowledge. Our planet itself also harbors its share of threats. Earthquakes, catastrophic events caused by the clash of tectonic plates, can happen at any time. Cities like Tokyo, situated at the junction of 3 tectonic plates, face a heightened risk of earthquakes. The cataclysmic effects of earthquakes were evident when Lisbon, Portugal, fell victim to massive tremors and a subsequent tsunami in 1755, claiming 60,000 lives. Another ever-present concern is volcanic eruptions. Despite advancements in science and monitoring, the unpredictability and power of volcanoes remain. A prime example is the 1980 eruption of Mount St. Helens in Washington, USA, which killed 57 people despite being monitored closely by government volcanologists. Even more alarming is the colossal volcanic hot spot beneath Yellowstone National Park, a supervolcano expected to erupt every 600,000 years, which last erupted 630,000 years ago. Its eruption could blanket a vast area in ash, resulting in massive disruption. Considering the inherent dangers we face from space and within our own world, our continued existence is a testament to our fortune and resilience. Our planet's precarious history serves as a persistent reminder of our vulnerability and the importance of remaining vigilant and prepared for potential disasters.
Having delved into the depths of A Short History of Nearly Everything, we've glimpsed the wonders of our universe, the astonishing vastness and the mind-boggling intricacies of the cosmos. We've followed great minds like Newton, Einstein, and Heisenberg as they changed the course of scientific understanding through their profound theories and discoveries. By establishing the connections between all living things and our common origins, we've recognized the immense value of biodiversity and the delicate balance of life on Earth. Lastly, we've become aware of the looming existential perils that lie in our celestial neighborhood and within our own planet, reminding us of our vulnerability and the immense privilege of being alive. This enriching journey has not only provided us with an awe-inspiring glimpse at the grand tapestry of the universe, but also a profound appreciation for the intricate, interconnected, and ceaselessly evolving miracle we call life.